Hello, everybody. My name is MAJERNÍK. I'm leading all quantum activities in ACCENTURE Slovakia. Now we are building quantum teleport for humans. If somebody wants to be teleported, please visit us. But unfortunately, we have some bugs. That means you probably know the movie, horror movie, Fly. You can assist us to help debug the systems. Just kidding. Okay, maybe you see this complicated title of my small light talk. Because the should be light talk, that means I have to handle somehow the light, and photons are particles of light. That means we have light presented here. And of course, the main topic of all conference is the AI. That means machine learning is a subset of AI. That means I have everything what we need for this light talk. And let me start maybe from the beginning. What is the machine learning? You probably know this very, very well, but basically what is the main strategy of machine learning? Always we try to find some functions, let's call it y, x, depends on the x, where x is some data sets. And with this function, without explicit programming, we're describing some data. We try to, let's say, separate this data to several categories. This is classification, or we will try to link somehow this data. That means we are doing some regression when, for example, when we want to something forecast. And we have several types of machine learning. Supervised learning, which is most common. You probably know many algorithms like support vector machine, this kind of stuff. That means you have data and somebody labeled data for you, or you already did it. You have unsupervised learning. That means you have only data, and your system should recognize what feature is important for you or not for correct classification or whatever. And the last is the reinforcement learning when you have nothing. That means you have to collect data during your training. Typical learning works like this. That means you have some cost functions. This cost function is describing your approaches to how to find your function. And usually you have several approaches in this ways. That means, for example, for supervised, it's quite simple, as you can see in this formula. But for unsupervised, usually you need to find some probability function which describe your data, your data sets. And sometimes quantum computing can help you, especially because you know the origin of quantum world or quantum mechanics is probabilistic. That means you can find these probable systems, and in this case you usually reach overwhelming classical computers. Support vector machine, as you can see, is very common. Supervised machine learning algorithms works mainly for classification. It's fine because it works for multidimensional data, and typically it's used for classification. That means, for example, you want to classify, is this patient for this diabetes somehow disposable or not? Or for example, is this picture contain something which looks like cancer cell or not? And this kind of classification, and this can be done very well with these support vector machines. Typically, in supervised learning, you know this when you have some, let's say, binary data. That means you want to describe and classify dogs versus cats or alligators versus elephants or whatever. And typically, in support vector machines, you have data represented with points, but these points are multidimensional. That means you have many, many features. Like, for example, when you are doing classification for diabetes, you have many features from the medical point of view, like the blood pressure, BMI index, or whatever. And you are using multidimensional space. And multidimensional space is very nature for quantum computers also. One benefit of the support vector machine is they can split with the line or a hyperplane your data. But usually many data are not linear, like support vector machine use this linear splitting between. What we can do if our data is not linearly separable? We can apply nonlinear transformation, as you can see in the picture on this pattern expression. That means this gives you another space or another extension for this your space, and you can apply your hyperplane like in this picture. It's simple to do it for example, in Python. When you have some representation of your data, you can use some, let's say, labels. You can use very simple Python SVM fit functions. But instead using directly on the X, you can use this nonlinear transformation and apply this linear fitting here, and it's simple to classify with this way. But many times happens you are not able to recognize your nonlinear transformation. You are not recognizing, for example, how to do it, or many times it's very expensive from the computer resources. Apply your nonlinear transformation for every data, for entire your data set. Due to it's better to understand how this works, and using this instead this transformation for each data, just use some inner product between. And this inner product, this inner product that just compare your vector with another vector, and it's just obvious or classical inner product. It's called kernel. This is the kernel trick. With kernel trick, you can represent a lot of things, like for example, linear kernel, it's represented with simple inner product. You have polynomial kernel, which when your decision boundary will be some curve, like you will see on the sinus or cosinus or whatever. And for infinity dimensional space, you can use very specific kernel, or not really specific, but very common kernel, which is called Gaussian kernel. It's Gaussian formula here, something squared. And we know from theoretical physics and from the linear optics that in laser beams world, there are some, let's say, squeezed coherent states. This is terminus technicus. What does it mean, coherent? You know, these coherent states or coherent lights from the laser. Coherence means between the states there are some phases, and the phases are somehow correlated. With this stuff, you are able to use this formula, and this is natural formula for each state, which is based on this coherent squeezed states, and you can recognize again this Gaussian formula here. And due to it's very simple to use photonic quantum computers, which using this squeezed coherent states in nature form, because they are already embedded in the feature space. That means they are already implemented this nonlinear feature. And you have to only use also your linear hyperplane how to split this. You probably know this picture from providers like Xanadu or any other, which using this kind of maze when you have a lot of optical devices with just splitting lights or doing some interferences between. And they are doing very interesting experiments to simulate its so-called Gaussian boson sampling. But this is a different topic. Main result of this light talk is this kind of computer, because they are using in nature extended feature space with these Gaussian states. It's simple to use for machine learning, for quantum machine learning, to use it especially in the support vector machines. That's all. You have some time for quantum superposition of questions and answers. And that's all from my side.